Okay, so now we're going to do that same kind of analysis that we did with mass. We're going to apply it to momentum. So we're starting here with Newton. F equals, this is F equals ma, or F equals change in momentum, and it's actually more rigorous form. And so we're going to consider again this control volume, identified control volume, and we're just going to rewrite this Newton's law in terms of these integrals. So we have the sum of the forces on the left, obviously. This is just the forces over here, and that's going to equal the change in momentum. But there are two ways momentum can change in a control volume. The control volume itself could change momentum, so the control volume could move, or it could change size or mass. So it could change its mass, it could change its velocity. So all those things are possible. That's what this is, the change in the control volume's momentum. But it also could have momentum entering or leaving the system. So, as fluid enters and leaves the system, it's going to take momentum with it or bring momentum with it, which could also, change the system's essentially overall momentum balance. So that's what we've got here. And we can do this, this is a vector equation. Notice there are vectors everywhere here. So vector, vector, vector. The dot product actually is not a vector. It ends up being a scalar because it's dotted, but we still have a free vector in each term, which means this applies to x, y, and z. So I'll go ahead and write this out for x, y, and z, though hopefully you'll see in each case, they're obviously equivalent to each other. So for the x momentum equation, we would have the forces in x, the net force in x has to be this time change of the control volume of u. Now, this is not a vector. This is u, little u, representing the x velocity times the density times the integral over the volume plus the integral over the surface of that same x velocity times rho, now times the u vector dotted with the n vector dA, integrated over that surface, or ds. And the y value, it's the same, right? So you're going to have the control volume integral, and it's going to be, but not u this time, it's going to be v, because v is the y velocity. So we have dv, and then we have integrated over the surface, but we have v here, rho, but u is still the vector here because we're still doing the dot product. So that's your term for the y forces, and then the z forces, or the z momentum equation, d, and then we use w for this one. So w is the z velocity, rho dv, plus the integral over that surface, w rho u dot n dA. All right, so those are our three force equations. As I said, this all relies on u being equal to u, v, and w. So this is your x velocity, y velocity, z velocity, which we've used before, but just to remind you. So that's that. So we're going to go back, and we're actually going to consider the same nozzle that we considered in the last example, but now we're going to do a momentum analysis on that. So we're going to consider the same nozzle as before. So we'll draw it again. Here's our nozzle coming down to a smaller diameter outlet, makes it a nozzle. I'm going to put some coordinates on now, though, because they matter to us now, because we've got x, y, and z here. So there's our x and our z, and you use our right-hand rule to get our y going in the right direction there. So we have x, y, and z. We're going to have the uniform inlet velocity. We know that. So this is going to be, that u in is equal to 0.5 meters per second. So this is an x-only velocity, and it's traveling at 0.5 meters per second. We know that the diameter in is 0.08 meters. We know that the average V out, so it's the U out, sorry, the average U out with a bar over it here is equal to 5.12 meters per second. And we know that the diameter of the outlet is equal to 0.025 meters. So we know all of that, and we're asked, and the problem will be, let's find the force required to hold the nozzle steady, right? So we want a steady nozzle here. So in order to do that, we're going to consider all three directions of force. We have X force, Y force, and Z force. I'll draw my control system here. Of course, it's just the nozzle. I hope it's obvious to everyone that there simply is no net force in either y or z. There is no real z velocity in this problem of some substance. There is z velocity in here as the thing goes, towards the nozzle, but it's exactly the same on both sides. So you're going to have as much upward as downward. Same thing for y. There's just no net thing happening in z or in y. So Fz and Fy are 0. V equals W equals 0 basically at the inlet and outlet at the very least. At the inlet and the outlet at the very least, V and W equals 0. And that's actually enough for us to say that Fz will be 0. So if we set W equal to 0, obviously both these terms go to 0 at the inlet and the outlet. So that Fz is going to be 0 at y, V is going to be 0 at the inlet and the outlet. That's going to cause Vy to go to 0. So we can conclude actually rigorously that Fy and Fz are 0. But Fz is not going to be 0 because we have U velocities at the inlet and the outlet. So that's what we're going to be focusing on. I'm sorry, Fx. So Fx is the only non-zero term. I'll write down Fy equals 0, Fz equals 0. Then Fx is equal to the change in time of the control volume momentum, U rho dV, plus the surface integral, U rho U vector dot n hat dA. But this is what we're saying. We're trying to hold the system steady. So that's what this is going to go to 0 to hold steady, right? So we're not letting the momentum of the system change. The system is supposed to not move. So we're going to let that's going to go to 0. There's going to be no change in time of the U velocity or of the density because it's incompressible or of the volume. So that's all going to 0. So rho is constant and volume isn't changing. U is constant in time. So U is changing in space, but it's not changing in time. It's going to be steady nozzle flow, so it just keeps happening. So no change in U over time, and no volume change. So that whole term is going to go to 0. So we're left with just the other term. So the other term gives us f of x is equal to the integral over that surface of little u here. This is the only x velocity times u vector dotted with n dA. So we're going to integrate over the inlet and the outlet. And we know that u is constant over the inlet. So that we already know. So we can pull that one out right away. So we have fx equals u in rho minus u in over the inlet area. And this, of course, is the u vector dot n hat, because we saw in the last example that u in is going this way in the inlet and the n hat is going the other way. So that's going to give us a negative sign. So that's going to pop that negative sign in there. So that's giving us that. And then, of course, this is just u in there, rho there, and that's the product. That's that u dot n term. So that's easy. And then the outlet, we're going to say, okay, yeah, well, we don't know the outlet velocity detail, but we can use this average outlet velocity. And so we're going to do that. And we're going to say this one is not, sorry, that's not a vector. It's an average. So we have the average outlet velocity times the area of the outlet. So this is that, u dot n at the out. This is the inlet. And this is the outlet. And at the outlet, that gives us a positive sign because n hat and u out are in the same direction. So there's no change in sign there. So it's just average u out times rho times average u out times the area out. So we have all these numbers now. So we can go ahead and plug these in. We got fx equals negative 0.5 meters per second. That's weird. Yeah, no, it's going to be, negative 0.5 squared, negative sign, 0.5 seconds squared times 1,000 kilograms per meter cubed times 0.08 over 2 squared times pi. There's nothing there. And then we have 5.12 squared meters per second squared times 1,000 kilograms per meter cubed times 0.025 over 2 squared pi. So that's our x force. Fx comes out to be 12.86 newtons minus 1.257 newtons equals 11.6 newtons. So we learn from this very simple analysis, again, very simple algebraic analysis, in order to hold that nozzle steady, we need to provide 11.6 newtons of force. So it's a good result from a simple algebraic result. Still, we don't know the details of the flow in terms of what the actual outlet velocity profile is, but we do know that if we were designing this nozzle, we would need to provide 11.6 newtons of force to keep it from moving.